Hi student, here I want to discuss about the solution for question B1 for the tray tower. The question is about to remove hydrogen sulfide from the light refinery hydrocarbon before the gas is further processing. So we are given here the mole fraction of hydrogen sulfide is 3.5 mole percent, and we also given that 90% of the hydrogen sulfide will be removed by using scrubbing, and the solvent that is given here is called aqueous weak basic solution, and it is pure. The absorption column is operated at 25 degrees Celsius and 101.3 kilopascal. And in this process, the feed gas rate is given as 50 kilogram mole per hour with the concentration of hydrogen sulfide in the absorbent solution leaving the tower is given as 1.5 mole percent. We are also given the equilibrium relation, which is y equal to 1.95x. So our job is to determine the solvent flow rate and the number of theoretical plates or tray used for these questions. So from the questions, we're going to substitute all the data. For the solvent, V1 is for the raffinate, Vn plus 1 for the feed gas, and Ln for the extract. So based on the question, we are given that the mole percent of hydrogen sulfide is 0.035. The concentration of the solute in the solvent or at the extract is given as 0.015, and the removal is only 90%. So we have 90% out of 100% that we have from the feed gas. So better we represent the symbol here, H2S represented by symbol A. C, the solvent, is the basic solution. So the basic solution here is given, and B will represent other gases. Okay. Since what is given here is the solvent used is pure, therefore the mole fraction for XCO is equal to 1. So we now can determine the XA0, which is the mole fraction of the solute at the solvent is equal to 0. So we need this data. Basically, before we can proceed with the graphical method to determine the number of theoretical stages, we need the information from XA n, YAN plus 1, XA0, and we also need the value for YA1, but we don't have this value yet. Okay, from the questions, we're going to substitute the data in the schematic diagram. So we need to draw the schematic diagram and label all the streams involved. That will be your streams for the solvent, L0, the stream for your raffinate, V1, the stream for your feed gas is Vn plus 1, and the stream for your extract is Ln. So we're going to represent the symbol for the solute, other gases, and the solvent. Alright, since in these questions, the hydrogen sulfide is our solute, so we're going to substitute A as hydrogen sulfide, and B is the rest of the gases in the feed stream, and C would be the solvent, which is our basic solution in this case. Okay, now, so in this schematic diagram, when you transfer your data, so you're given the solvent is pure solvent, therefore Xc naught equal to 1 and Xa naught equal to 0. So no flow rates that consists of solute in the solvent stream. And we also given the mole fraction of the solute at the feed gas, which is 0.035. In the feed gas, we have VAN plus 1, which is the flow rates of solute, and VBN plus 1, which is the flow rates of the other gases. And it is given 50 kilogram mole per hour. In the extract part, we have the information on the 90% of the solute. So 100% is come from VAN plus 1. So therefore 90% out of VAN plus 1 will be the solute recovered at the extract. And the amount or the mole fraction of the solute at the extract is also given as 0.015. But there's not much information as your as the mole fraction for the raffinate for the solute that we have, but we can still calculate it in the future calculation, so not to worry about that. And we're also given the equilibrium relationship, which is 1.95x. Okay, now let's proceed with the calculation, further calculation. With the information given for YAN plus 1 and the flow rates of the feed gas, now we can determine the mole fraction of the other gases, which is 1 minus 0.035, so that we get 0.965. And then from this information, we can calculate the flow rates of the other gases and the flow rates of our solute, which is VAN plus 1. So it's also given previously that the recovery of solute in the extract is 90% out of VAN plus 1. So therefore now we can determine the flow rates of the solute at the extract is 1.575 kilogram mole per hour. From the questions, we need to determine the solvent flow rates, which is in liquid form. Therefore, from here, we can determine the flow rates of LAN, which is LAN is given by LN is equal to LAN plus LCN. So from the mole fraction given, we know that XAN is equal to LAN over LAN plus LCN. So the objective here is actually to find LCN, because LCN is the flow rates of the solvent. So once we get this LCN is actually equal to L naught, which is the flow rate of the solvent. So let's do the substitution. XAN 0.015, LAN is 1.575 divided by LAN, which is 1.575 plus LCN. So from here, we should get the value of LCN is actually equal to, it's 103.42543 kilogram mole per hour. So that's our answer for the part 1. Okay, for the answer part 1, we know that L naught is equal to LA naught plus LC naught, but no flow rates of solute in the solvent. We just have the pure solvent. So therefore, LC naught is also equal to LCN that we get from here. So lastly, the LC naught equal to LCN is equal to 103.43 kilogram mole per hour. So this is to answer the first part. Okay, we still have one more fraction for the raffinate part that we don't have the value. So we need to find YA1. So we have XA0, XAN, YAN, and we need to find YA1. So in order to calculate YA1, we need to calculate V1. So V1 is equal to VA1 plus VB1. But from the questions and from the calculation, we have calculated that YBN plus 1 is equal to 0.965, which is equal to 48.25 kilogram mole per hour. So this will be the flow rates of other gases, and that will be the same flow rates of gases, other gases, go through the raffinate. And then we know that only 10% of solute released at the raffinate. So we can calculate our flow rate for the solute here is equal to 1% multiplied by 1.75 that we have from the feed gas. So total that we get for V1 is equal to 48.43. Therefore, it is possible to calculate YA1, where YA1 is equal to VA1 over V1. So we get 0.036 for YA1. So now, the data that we have are completed. We have two coordinates. One is from the bottom of the column. Another one is come from the top of the column. So this is to simplify the value that we have in order to calculate the number of tray or stages graphically. So we need these two coordinates. So these are the representation of the coordinates that we have. The bottom of the column consists of XAN, YAN plus 1, and the top of the column is XA0 and YA1. So now we can draw the graph. So we need the information for the equilibrium line, and the equilibrium line is given by the relationship of y equal to 1.95x. Therefore, we just make substitution. When x equal to 0, we get y equal to 0. When x equal to 0.016, we get 0.0312. So you need to be careful what would be the scale that you want to use or to substitute the value of x here so that everything lies in the graph. So we have these two coordinates to represent. So we have at the bottom of the column coordinates that will represent the top coordinates at the operating line, and the coordinates for the top of the column that will correspond to the bottom coordinates for the operating line. So we need to draw this graph. So from this graph, we can see that we have a straight line for the equilibrium. So you can extend the line, no problem. You just extend the line. When you have the two coordinates here, the one that you have calculated or substitute in the given equation, just extend the line, and then we plot the coordinates from the calculation. So you can just extend the straight line, but we have a limit here, whereas our limit is xan. So this is our limit. The orange line represents the equilibrium line, and the blue line represents the operating line. So from the graph, we can label our graph. So this is the coordinates for yan. So we just move this point and just label the point. Next is to get the label for the bottom of the operating line. Next, what you need to do is start drawing your horizontal line here, and a vertical, horizontal, vertical, until you reach the limits that we have. Okay, just continue our triangle. So this is tray number 1, number 2, number 3, 4, 5, 6, and 7. Since tray number 7 exceeds the limit of xan, so therefore we're going to estimate the length that we have. So this would be our total length, and this would be our length. So this length divide with the total length, so we get approximately 1/3 or 2/3 of the length. So therefore the answer for the total theoretical tray would be around 6.7. So that will be the result that we have. So this is based on my graph. So you might get around this value, okay, but not far from this value. Alright, thank you very much. Please enjoy doing the tutorial questions and try again for the other types of questions. Thank you.